So this video shows how to solve exercise 31 in section 2.1 using Maple. And in this case, we're going to see how to do a plot of a differential equation, a direction field, and also how to solve the differential equation. And then we're going to see if we can figure out what's happening in this problem. So in exercise 31, we want to solve the IVP and describe how the initial value changes the nature of the solution. Okay, so I've got some stuff already written out. The first line I like to have with plots and with DE tools. That gets me ready. And remember how to enter a differential equation into Maple. It's the derivative now is diff y of t comma t. And then we have our minus 3 halves y equals 3t plus 2e to the t. And again, that's just the differential equation that's given to you in exercise 31. Okay, so now we will, I better make sure I've hit that. Now we're going to do a direction field to see what's going on. Now I've had to do a little bit of trial and error to make sure that I had a good window size here. Let's go ahead and see what I've got. And so this example here is to show that there is a difference depending on y of 0 as to whether the solution will be going off to positive infinity or negative infinity. And so here you can see that if y of 0 is this slight negative number, in this case y of 0 equals minus 1, the solution does go off to positive infinity over time. Here, if it's equal to 1, it goes off to infinity. We see from the direction field that these are also going off to positive infinity. But now down here, if y of 0 equals minus 10, suddenly everything's dropping down to minus infinity. So somewhere in between these two, there's a break in the solution to the differential equation. And so that break is going to depend on the initial condition. And so let's solve the differential equation then for y of t. And here we see what the solution to the differential equation is. Notice I'm setting y of 0 equal to a here. And let's take a look at this. So this plus e to the 3 halves t term is going to dominate this expression if this constant right here is not equal to 0, right? Because the e to the t term isn't going to overpower the e to the 3 halves t term. Okay, so our solutions then will depend on just this term. Just this term with the a plus 16/3. And so we can see what's going to happen now if this constant right here is equal to 0. Well, you can see that if this is all zeroed out, right, then our solution is going to be going to minus infinity because of the minus 4e to the t. But if this is positive, then this positive number is going to make things move to positive infinity over time. If this is negative, things are going to negative infinity over time. Okay, so things are going to change then right at 16/3. Okay, and so remember how to, if we wanted to get a numerical value for that, remember how to do that? Just a little review. That's 5 1/3. Okay, so or that's, I should say minus 5 1/3, right, is where the break occurs. So let's try a minus 5 here and see what happens. See, that's going to minus infinity, but then what happens if I put in minus 5.34? Maybe a little bit more than that. The numerical issues are going to overtake us here. There we go. I'm going to need to make time go a little bit further. Let's go ahead and make it minus 6, just to make sure that it goes here. Oops. How about minus 5? Minus 4. There, it starts to bend. Okay. So that took a little bit of trial and error, but because we're only going to time 2, right, the pull up to positive infinity has to take place pretty quickly. We could change that to 10, for example, and then we would really see it. So for example, if this was minus 5 now, oops, the numerical error is still sending it off to minus infinity. Although it should be going to positive infinity at some point, minus 5 point. Oh, that's fine, for 4.5 there. So that's about as close to that as we can get and still pop to positive infinity here. Otherwise, numerically, there might be an issue. Okay, so anyway, we see that numerically we may not be able to see it exactly, but just from our computation here, we can see that the value that we want is 5 1/3, minus 5 1/3. Okay, so that solves problem 31. The other ones are very similar.